which is simple harmonic motion in waves. So we have studied in second chapter of ninth physics that motion and its types. So here we shall study another type of motion, which is simple harmonic motion. So let's categorize it. We studied in that chapter that motion is divided into three types. One of them is vibratory motion, which is to and fro or back and forth motion of an object, and its special type is simple harmonic motion. So simple harmonic motion is special type of vibratory motion. And how can we differentiate simple harmonic motion from other types of vibratory motion? So for that difference, let's define it. Simple harmonic motion is such a type of vibratory motion in which acceleration is directly proportional to displacement from mean position and is always directed towards mean position. So here we are using another term, which is mean position. So we need to identify that mean position, then we can properly understand this simple harmonic motion. For that, let's draw a diagram for vibratory motion. For that, if we take pendulum of a clock, then that point at which it comes to rest, that is its mean position. So this point is mean position. When it starts vibrating, then it starts moving sideways, left and right. So when it moves from this original position towards this side, let's say it comes to this point A, then the maximum distance which it attains from this original position, it is known as extreme position. And this position where it comes to rest, it is known as mean position. So this is mean position. How can we understand this definition? Such a type of vibratory motion in which acceleration is directly proportional to displacement. Let's take its first part. If this mass is moving from this mean position towards this extreme position, then its acceleration will be directed towards mean position. That is, direction of this acceleration will always be towards mean position, whether object is moving towards extreme position or it is coming back from extreme position towards mean position. So direction of acceleration is always towards mean position, and acceleration is directly proportional to displacement from mean position. That when this object is moving from mean position towards extreme position, its displacement is increasing. With this increase in displacement, its acceleration is also increasing. So this is the definition of simple harmonic motion, that with increase in distance from mean position or with increase in displacement from mean position, acceleration also increases. And direction of acceleration is always towards mean position, whether object is moving from mean to extreme or extreme to mean position. First example which we will have to explain, that is motion of mass attached to spring. So we shall take a mass which is attached to spring and then apply this definition of simple harmonic motion on that particular mass. If we take a mass attached to that of spring, then let's say it is initially at rest and it is at position A. When we stretch this mass, then it comes to this point A, and when we release it, then it starts oscillating between points A and B. That is, it goes back to this point, let's say B, and then again to A, and starts oscillating between these 2 points. Then its motion is simple harmonic motion, and we shall apply this definition, and we shall also discuss that why does this mass continue its motion and for how long will it continue its motion, and if it continues its motion for a certain period of time, then how can we find its time period. We can apply Hooke's law on this mass, because when we stretch the spring, then it exerts an opposing force. So let's say that this spring is stretched through a distance x towards right, and its distance would be same on left hand side when it will move towards second extreme position. So we know that by Hooke's law, when we apply an external force F, then this force is directly proportional to displacement. That is, if we will increase the quantity of force which we are applying here, then displacement would also increase. So F is directly proportional to X, that is force is directly proportional to displacement. We can also write it in this form as F is equal to Kx, where K is proportionality constant, or it can be written as F is equal to minus Kx. Why we have written this minus sign? This is because when we apply a force F on spring, then spring exerts a force back which is opposite in direction to that of applied force. So this minus sign shows that spring applies an opposite force. So we can write it as, for K, we can write it as K is equal to minus F divided by X, where this K is a constant and this K is known as spring constant. Now, what is a spring constant? We can define it from this equation. We can define this spring constant from this equation number 2. You can see that K is equal to F over X. That is, it is the ratio of F and X, where F is applied force and X is displacement. So we can define spring constant as ratio of applied force to that of displacement is known as spring constant. So what would be its unit? We can solve it here that K is equal to, unit of force is Newton, unit of distance or displacement is meter, so unit of K is Newton meter inverse. This will be the unit of this spring constant. But what does this, what information do we get from this K or spring constant, and what does it tell about the spring? This K is stiffness of a spring, that is, the value of K tells us about that how much stiff or how much soft a spring is. So value of K tells us about stiffness or softness of a spring. So if you are asked generally that what is spring constant and what information do we get from it, so a spring constant always tells us that how soft or how stiff a spring is. And if we can also define it from this equation, but that definition does not tell us about the nature of K. We need to draw that figure again, because description of this question is just discussion of that figure of mass spring system. So we shall draw that figure again and we shall label it, and we shall also discuss that what kind of forces are acting. Let's say this is the original position of spring. When we apply a force F on this spring, then it is stretched, and let's say it comes to this point A. And when it is released, then it starts oscillating and it comes to this point, let's say B on this side. Now we can label this figure here. This is original position, and these two are positions when spring is stretched or compressed. So this position which is obtained when we stretch the spring, this is known as extreme position. This position where this mass reaches when we compress the spring, it is known as extreme position. So we can say that in mass spring system there are two extreme positions, A and B, and there is one mean position which is O. When we stretch this force, when we stretch this mass spring system, then the force which we apply, that is known as force applied or applied force. But when you stretch a spring, you always feel that spring is exerting a force back. That force which spring is exerting, that is when we are stretching the spring in this direction, spring exerts a force in opposite direction. That force is known as restoring force. So it is very important factor in this motion, restoring force. How can we define it? Restoring force. How can we define it? Applied force is that force which is applied externally on a mass spring system, and restoring force is that force which always attracts the mass towards mean position. It means that when we shall attract the spring towards point A, when we shall stretch this mass spring system towards point A, then restoring force will be directed towards O, that is towards center. And when this mass spring system will move towards point B, then direction of restoring force will again be towards A. So direction of restoring force is always towards mean position. It is always a force which is always directed towards mean position. So one definition of restoring force is that force which is directed opposite to that of applied force, that is known as restoring force. In second definition is that uh, a force which is directed towards mean position, that is known as restoring force. You need to write these definitions on your book. So write these definitions on your book, that a force which is always directed towards mean position, that is known as restoring force, or a force which acts in direction opposite to that of applied force, that is known as restoring force. When we stretch this spring towards point A, then it starts oscillating between points A and B. Restoring force stretches the mass towards point A, then why it does not stop at point O? It is because of inertia. Then what is inertia? Inertia is that characteristic of a body due to which if object is carrying any uniform motion, then it continues its uniform motion. So this mass spring system has uniform motion once it starts moving from point A towards B. As it is possessing uniform motion, then it does not stop at point O due to inertia, because inertia is its ability to move, to continue its uniform motion. That is why it continues its uniform motion. And when it crosses this point O and starts moving towards this point B, towards second extreme position, then direction of restoring force changes. Once it was in this direction, when this mass spring system was moving from A to O, and when it crosses point O, direction of restoring force becomes opposite and again is directed towards this point O. So this is the explanation of mass spring system, that why does this motion occur? Once we stretch the spring, once we apply the force, that is applied force, and leave the spring, then a restoring force is developed, which is always directed towards mean position. But once mass reaches mean position, then it does not stop due to inertia, because inertia carries the mass to continue its motion. So these are the factors which are involved in motion of mass spring system in its simple harmonic motion. Applied force, restoring force, and inertia is the ability of a mass due to which it does not stop at point O and it continues its motion about point O. So we can check that definition which we wrote at the start, that direction of acceleration must be towards mean position. We can see that when object starts moving from O to A, then its velocity goes on decreasing. Because its velocity goes on decreasing, then it comes to rest at point A. We know that once velocity is decreasing, then acceleration has direction opposite to that of motion of object. So we are moving the mass in this direction, and as its velocity is decreasing, so direction of acceleration would be towards O here. So while moving towards A, point A, direction of acceleration is towards point O. Once object starts moving from point O to B, again its velocity starts decreasing and acceleration would be directed opposite to that of motion, that is its direction will be towards point O. So these are the cases when object is moving away from point O, we have seen the direction of acceleration will be towards point O. Once object is moving from point A towards O, then we know that object comes to rest at point A and then it starts moving. So it gains some velocity. From 0, it gains some numerical magnitude, 1 or 2 or 3 meter per second. That is, its velocity goes on increasing. So when velocity is increasing, then direction of acceleration and motion are same. So object is moving from point A towards O, so its direction of acceleration will be same, and same happens on this from this point B. So we can see that in all the cases direction of acceleration is towards point O. Second, when this object moves from point O towards A, acceleration must be directly proportional to displacement according to definition of simple harmonic motion, and it does happen. When object is at point O, it always possesses uniform velocity. Whatever velocity it is possessing in during first cycle, it possesses same during second cycle, same during third cycle. But when it moves towards point A, then its velocity changes maximum, and we know that maximum velocity is not acceleration, maximum change in velocity is acceleration. So let's say if velocity is 4 meter per second here at O and 0 meter per second here at A, then it changes maximum. So due to this maximum change which is occurring at extreme position, so we can say that acceleration is directly proportional to displacement, that is with increase in displacement from point O, acceleration goes on increasing. So we can say that this example of mass spring system, it fulfills the definition of simple harmonic motion. So it is an ideal case which obeys a simple harmonic motion of objects. Now we shall again draw this figure and we shall label energy changes, that what energy changes take place during this simple harmonic motion of an object. This is mass spring system. It is at rest at this point, mean position, and these are two extreme positions. So when this mass is brought to this point, extreme position, let's say point A, which we have labeled here, point A, then it comes to rest at this point. Whenever object comes to rest, then its velocity is 0. We know that kinetic energy is given as 1 by 2 mv square. So putting value of velocity 0, then we have kinetic energy is equal to 0. So at this point we shall have value of kinetic energy is equal to 0. Why? Because velocity is equal to 0. And potential energy, we know that potential energy is maximum when object has maximum displacement. In this case we shall not use formula potential energy is equal to mgh. For such cases we have formula potential energy is equal to 1 by 2 kx square, where k is spring constant which we have defined earlier and x is displacement from mean to extreme position. So we know that here displacement is maximum from mean position, so potential energy will be maximum. And acceleration is maximum. At mean position, object moves, it does not stop, so it has maximum velocity at this mean position. When velocity will be maximum, kinetic energy will be maximum. Putting the value of x here, at mean position value of displacement is 0, x is equal to 0, and if we substitute this value in potential energies equation, then potential energy becomes 0 and acceleration becomes 0. And labeling for this extreme position would be same as that of other extreme position. Kinetic energy is equal to 0, velocity is equal to 0, potential energy is equal to maximum, and acceleration is also maximum. One important question from a board's paper point of view is that what is restoring force in mass spring system? That which force is bringing this mass from point A towards O? Which force is stretching it? So that force which is stretching it towards O, that is restoring force, and that particular restoring force is known as force of spring. So force of spring is restoring force in case of force of spring is restoring force in case of mass spring system. So note it on your books. Second example which we shall take to check whether that is possessing simple harmonic motion or not, that is ball and bowl system. Ball and bowl system is this type of a system in which we take a bowl and we place a ball in it, and when this ball is placed at this point A, then it starts moving and it comes to this point O and then goes to another point B. Then what changes do take place and what is restoring force in this case? So originally ball is at point A, we apply a force, that is applied force in this direction, and we bring this ball at point A. Once this ball is brought at point A and released, then it starts moving towards this point O. Why does it come towards point O? It is due to restoring force. Which restoring force is acting in this case? In previous case it was force of spring. So here restoring force is force of gravity, that is attraction of earth or weight. Gravity is also weight also known as weight here, force of gravity or weight is the restoring force in this case, which is stretching this ball towards point O, but it does not stop at point O again due to inertia, because it is possessing uniform motion, and inertia is that ability of a body due to which it continues its uniform motion. So it crosses this point O and goes back towards point B. It stops at point B. Why? Because Earth is exerting an opposing force. Ball is moving in upward direction, Earth is attracting it in downward direction, and there comes a point at which it stops. This is its second extreme position. It is extreme position. It is also extreme position. In every simple harmonic motion there are two extreme positions and a single mean position. Mean position is that one that if object is brought to rest, then it comes to rest for a longer period of time at mean position. And there are two extreme positions as well in this motion. Restoring force is gravity or weight, which is due to Earth, which is attracting this ball, and restoring force is again opposite in direction to that of applied force, which is same as previous case. So now we shall discuss that what are the energy changes which are taking place. So for energy changes, draw a separate diagram and label energy changes which are taking place. So at point A, object comes to rest, and if object comes to rest, then its velocity is 0. If velocity is 0, then kinetic energy is 0. But displacement is changing maximum from point O to this point A. If displacement is changing maximum, then acceleration is maximum. We know that in simple harmonic motion, acceleration is directly proportional to displacement. So if displacement is maximum, then acceleration will be maximum. And we know that all other points which are before point A, this point, this one, or any other point before point A, that has displacement less than that of point A. So at point A, displacement is maximum. That is why acceleration is maximum. And potential energy will also be maximum. In this case, which formula we shall use for potential energy? That is, potential energy is equal to mgh, because h will be the height of this ball, and which is maximum at point A. So with increase in this height, potential energy becomes maximum. So these are the labelings of energy changes at point A. Energy changes and velocity and acceleration changes will be same at this point B, because both are extreme positions, and at all extreme positions values of velocity are same, values of kinetic, potential and acceleration, kinetic and potential energies and acceleration is same. At mean position, we know that object possesses maximum velocity. When its velocity is maximum, because it comes at high speed from this top, so it possesses maximum velocity. When velocity is maximum, then kinetic energy is maximum. Whereas at this point its height is 0, because it was possessing some height from this point, but it is placed on ground, so its height is 0, which means its potential energy will be 0. And its acceleration will also be 0. Why? Because at this point its displacement is 0. We know that acceleration increases with displacement in simple harmonic motion. So it is not possessing any displacement at point O, because displacement is always calculated from point O. When object is at point O, then it has no displacement. So when it is not having any displacement, then its acceleration will be 0. Remember